Hi, I'm Robert Hildebrand. I'd like to tell you about some joint work with Daniel Meanstock and Alberto Dobia. This work is called Complexity, Exactness, and Rationality in Polynomial Optimization, and you can find our latest version of the paper on arXiv. So I'd like to talk today about polynomial optimization problems, and I'd like to think about rationality within these problems and certifying optimal solutions or feasible solutions. So we'll talk mainly about cubic polynomials and linear constraints, but we'll see a few different variations. So consider some general polynomial optimization problem. Think about, are there rational solutions? Are there rational solutions also to the feasibility problems? Are there rational solutions that you can actually write down in some reasonable encoding size? How does complexity with polynomials differ, whether you have quadratic, cubic, or quartic, or linear for that matter? And lastly, how can we think about rationality when we deal with certifying or unboundedness and think of some directions? Okay. So I'll start with some easy warm-up problems, and then we'll talk about some complexity results related to these issues, and then we'll end with an example or two. Okay, important thing to keep in mind throughout the whole talk, we're thinking about computational complexity really in this bit model. So when I think about size of encoding, you can go back to Shriver or any other reference where you think about size of the numbers being coded as bits, 0, 1s, and ask if you have so many integers, how many bits does it actually take to write down these numbers, and think about that in terms of the input of the problem. Okay, so fun warm-up problems. Let's think about some maximization problems with some polynomial constraints or linear constraints even. So we know basic linear optimization, classical polyhedral theory says that there will be a rational solution if there's if the problem is bounded, and you can write it down in polynomial size. Once you have a quadratic constraint, you see that you quickly get an irrational solution, just maximizing some linear function subject to some easy quadratic constraint. But surprisingly, if you have a quadratic objective subject to linear constraints, you actually get rational solutions to this problem. This is known from Vivacis from the 90s, and there's a paper recently that interprets this thing as like a KKT condition problem. And you see the KKT optimality conditions are just linear constraints, and so the optimal solutions have to be cut out by some rational number, a rational point that you can describe easily. Okay, so lastly, you get to cubics, and things get bad pretty easily with cubic objective and a linear constraint. Okay, so I'd like to move to feasibility issues. So suppose I just have a polynomial objective and or a single polynomial constraint with some linear constraints. And you know, linear and quadratic, you can pull out rational solutions based off the previous arguments. Now cubic, this is a little more unknown, and we'll examine this a little closer. And then quartic, you can easily say that you have a single quartic constraint that only has irrational solutions. Okay, so easy stuff, fun examples, hopefully. That's going to be building up to what we can do in a positive sense, and then hit a boundary and say, well, this gets difficult, and then how does that trickle into many other examples? Okay, so what can we do? Well, if you have a cubic with that's univariate, and then you have some upper and lower bound constraints, say all the data is integer, then you can actually say there exists a rational feasible solution. Maybe this isn't surprising. Maybe it's simple and nice. So there's three kind of examples you might look at. There's the case where there's the two left cases that are pretty easy. So first of all, the far left case, if the set is somehow full dimensional, then you know that all rational points are dense within all the reals, so you're going to have some rational points sitting around. If the set we're looking at is actually a single point that intersects the boundary of our interval, then you know the boundary of the interval was actually integer originally, and so you have a rational point. So the third case is really an interesting case where the set is 0-dimensional. It's just a single point, but it happens to lie on the interior of the interval. Okay? And what do you notice about this? Well, it happens to be the minimum, or a local minimum of the cubic, and that seems to play in a nice way. So I'll show you a cute little proof here that shows you actually have a rational solution in this scenario. So the proof goes, well, first, let's do a shift to make our calculus easier here. So we say, well, without lost generality, b is 0 after doing some nice, easy shift. And that's an easy lemma to show, probably very well known. Okay, so we already said the first two cases were pretty easy, full dimensional or endpoint. So otherwise, let's think about this hard case. We'll look at the function and its derivative. And then we'll say, well, since the set is not full dimensional, we'll have that single point satisfy the constraint f of x bar is equal to 0, and x bar is our local minimizer. So what does this mean? Well, we set the derivative equal to 0 because it's a local minimizer, and you can solve for x bar being plus or minus the square root of this quotient here. Okay, so if you plug this back into f of x bar is equal to 0, you get an equation that you can massage a little bit. And then what you find is that the square root that you have is actually in a linear equation with a bunch of rational numbers. So this means that the root is actually rational in the end, in this one very special case. Okay, this is how you prove the theorem. It's a cute little theorem in 1D. You can actually generalize this to 2 dimensions, provided that you have a separable cubic inequality. So you have 2 variables, but the variables don't interact in your cubic at all. And you can generalize to this case. And now there's a few details here. So we're also going to add the fact that you can say there exists a rational solution of polynomial size. So in this case where you have like this interior, or it could be any point, you can actually argue there's one of polynomial encoding size. Okay, there's a few cute lemmas that you use. There's one about using some rational numbers in an equation, and if you sum these rational numbers in this nice specific format, and they equal a rational number, then you can actually argue that the square roots of these QIs are also rational. We also use some bounds from Cauchy. We could probably use some other bounds as well that just bound the size of roots of a polynomial, and this helps us figure out the size, the encoding size of a possible solution for the problem. Okay, I won't go into the details of that proof too carefully, so I can get on to fun examples. And I stressed that we really needed the separable case. And what you see here is that if you look at the non-separable case, you run into this issue. Okay, so here's our non-separable counter example. We did this in terms of y variables. And what you can see is that this has a local minimizer at an irrational point whose function objective value is actually 0. Okay. And so for the sake of this talk, for the sake of several proofs, I'm going to look at a box here we'll call r sub gamma, where the gamma parameter is just going to just lower the first interval here by whatever gamma is. Okay, so the observation here is that the inequality h of y less or equal to 0 and y in r sub 0 set has a unique irrational solution. So here's the picture over here, and then here's the actual set of solutions, which is the single point. And then we'll make the observation that, okay, if you enlarge the set, so I now look at r sub 4, so I increase my bounds a bit, then that actually has rational solutions. All right, so you can see that the set of feasible solutions over here is now full dimensional in this cell, and you can find a rational solution. And so we're going to use this in some proofs, and the first major theorem that we're going to talk about here says if you have this cubic inequality along with linear constraints, then it's actually strongly NP-hard to test if there's a rational feasible solution. Okay. And in fact, you can know ahead of time that the set is non-empty, and that doesn't affect the issue. It's still NP-hard to test if there's a rational feasible solution. Now, the key idea of this proof, we'll talk through this proof, this is the last main proof here, is to encode 3-sat in a way that uses our cubic function, and then we'll add a handful of quadratic terms here to help encode 3-sat. And then we'll add some linear constraints so that doesn't affect the problem too much. And now what we'll say is that if 3-sat is unsatisfiable, then my gamma parameter has to be small, meaning that there's going to be a single irrational solution. Now on the other side, if 3-sat is satisfiable, then we can allow gamma to be large, up to 4, for instance, and then you will get rational solutions. Okay. So let's walk through this proof. We need a few observations before we get into it. So first observation, as we pointed out, you have this irrational point y star sitting in this R sub gamma set, and I want to recognize that this point over here is actually feasible whenever my gamma is bigger or equal to 0. So if you increase gamma, it's always going to be feasible, and that's going to be a point we can think about. Secondly, it's actually the unique minimizer of the h of y function over all non-negative y values. Okay. And next, we need some bound. You can prove a tighter bound, but we said for r sub 4, when you look at this box, the objective function h of y is always bigger than -12. And you could adjust it to make the calculations better if you like, but it doesn't really matter in the end. And lastly, we need some rational point, which we just picked this one, and we'll know that it attains some value that's less than -7. Okay, there's our observations. Now, we're going to encode 3-sat. So what do we need? We need some literals. We'll call these W1 to Wn, and we need some clauses C1 to Cm. And we'll look at this formula, C1 and Cm, C2 on up to Cm. Now, for each literal Wj, we're going to create 2 variables. So first, variable xj that's bounded between -1 and 1. And then for the negation of the literal, we'll create some other variable, which we'll call x sub n plus j, which is also bounded between -1 and 1. And we want these to be negations, so we'll enforce this equality here where xj is the opposite of -xn plus j. Okay, now for a clause that looks like W1 or not W2 or not W3, I'm going to add the constraint that says x1 plus xn plus 2 plus xn plus 3 is bigger or equal to some lower bound, which we're going to write as -1 minus delta. Delta will be a variable here. So I'm giving you an example of how to model a specific clause, and you can use this template for other clauses, which you notice is the negation corresponds to the negation associated variable. Okay, and now we have gamma is going to be bounded by 0, delta is going to be bounded between 0 and 2, and then I have this inequality here that connects delta and gamma, where twice delta plus gamma is less than 4. What does this mean? If delta is equal to 2, or if delta is close to 2, it's going to force gamma to be close to 0. On the other hand, if delta is allowed to be 0, then it's going to allow gamma to range to 4, and you'll get a larger set of solutions. Okay, and now lastly, we're going to use this h of y function, and we're going to combine it, as I said, with some quadratic pieces, and we'll add them up like this. We'll see how this plays in just a second. Okay, so first thing to note, this point y star is feasible for this system, provided you pick the right xj's. And so if you say all the xj's are 1, and I suppose that means all the xn plus j's are going to be -1, this point is actually feasible for the set. So for any choice of gamma, or I guess regardless of what the clauses were, this point is feasible for the set. So now we're going to ask, based off whether SAT was feasible, can we get more solutions that fit in? Okay, so coming back to our observations, some things to point out here. First of all, we're going to look at this lower bound minus 12. We said this was the lower bound on the set here. And then second of all, we'll look at an upper bound here. So I want you to notice that this quantity here is actually less or equal to 0. And this is because we have a minus n squared, and we have a sum of n terms that are upper bounded by 1. And so you have it at most minus n to the 6th plus n to the 6th, which would be less or equal to 0. Okay, so let's use those bounds. So first of all, we'll use this lower bound of minus 12. And what I really want to enforce here is that the xj's are basically plus minus 1 variables. And not going to be exactly plus minus 1, but it's going to be close to that sense. Okay, so how does this work? We use this minus 12 and connect it to this part of the inequality. And now we know that if we do a little rearranging, we have the sum of xj squared, and we can say this is actually less than or equal to n minus 1, since we know each xj is bounded by 1, plus the smallest x that we have. And if we rearrange this again, we see that the smallest x that we have in absolute value is lower bounded by 1 minus some small number. Okay. This means that all the x's have to take values close to minus 1 and 1. Okay, so if a clause is not satisfiable, what happens? So consider this clause once again, that we have this constraint associated with the clause. So we must have that all of our x's are upper bounded by by this number here. Okay? So if it's not satisfiable, then all of these could not be satisfied, and then we end up with a bound like this. And so what does this imply about delta? Well, it says that minus 3 times this, we have 3 of them in the expression up here, is greater or equal to minus 1 minus delta. And as you see, it says then that delta is bigger or equal to some number, which is approximately 2. Okay, so if we combine this with our inequality now, it says 2 times delta, and now is closer to 4. And it says that gamma then needs to be small. So gamma in the calculation actually less than 72 over n to the 5th. And this means that there's actually only that unique feasible solution we looked at. Okay, so that says if any clause is not satisfiable, this is what's going to happen. Now, if all the clauses are satisfiable, we see that we can actually set this delta equal to 0 and allow gamma to range up to 4, and then we can find our rational solution that fits in our set. Okay, and that's the whole proof right there. This is the complete system. You see we have some inequalities and a quadratic and a cubic part of this inequality here. Okay, so we use this cubic inequality and this set here. And what I would like to stress is this example can now be used in a few different contexts. And so the first context I'm going to look at is consider a system with multiple quadratic inequalities. And you can add some linear constraints. And suppose you know the system has rational feasible solutions. Then you can actually argue that it's NP hard to test if there is a rational feasible solution of polynomial size. So, you know, it has rational solutions you can write down. It's actually unclear if you can write them down in a reasonable space. And I'll show you the motive in an example here. So we've seen a few other examples in literature where you have like this sequence of quadratics. And what we've done is reverse this in a way. So we're going to have some variables d. Our d1 is going to be less than 1/2. And then we're going to have this sequence of variables where the next d variable is always less or equal to the prior one squared. And what you see is this creates this smaller and smaller window of where these variables can live. And now we're going to have our s parameter be smaller than the biggest one squared and s be non-negative. Okay, so this means that either s is going to be 0. So you have either s is going to be like our boundary point here where it's 0, or you know that it's bounded by some number that's really, really small. It's exponential in the encoding size when you try to write this down. Okay. So either you have 0 or it's very difficult to write down any solution for the s variable. Okay, so if you add this to your system, so we add these inequalities, and then we sneak in our s into this cubic inequality, you actually obtain this result that it's NP hard to test whether you have a rational solution that you can write down or a rational solution that's of exponential size. And this needs a little work to get there. And I'll note there's also this transformation here that I'm just kind of sneaking under the rug, where I said in the theorem that you only had quadratic inequalities. Well, you can always take a cubic inequality, add some equations, and get only quadratic inequalities. Okay, so what else can we do? You can have issues with the optimality or the superoptimality of nearly feasible solutions. So we know in solvers and computational solvers that often you look for like an epsilon approximate solution that satisfies all the inequalities up to some epsilon guarantee. And what I'd like to stress is that it can actually, you can actually have a very super optimal solution if you allow this extra epsilon to take hold. And furthermore, if you have this epsilon feasible solution, it could be very difficult to test whether or not it's actually optimal or whether it's infeasible but super optimal for your problem. Okay. And so the mode of an example here is something in 2 variables with some quadratic inequalities. And we have an s parameter again. And so the picture looks like this. So I have 2, I guess, concave quadratic inequalities here. And the s is going to adjust the size of one of these here. And then we'll have a third inequality here. And what we get is when s is 0, there's actually a feasible point sitting right here. I guess this is z1 is 0 and z2 is 2. And otherwise, when s grows, it bumps out one of these inequalities just a little bit, making that point infeasible. And now the next feasible points are actually quite a bit lower in terms of the z2 objective. Okay. And so you can argue this theorem by using this example here where you maximize z2, you maximize the z2 direction, and then you tack on this whole system in all these other variables that we dealt with before. So the proof is very similar, but there's a few technical details to get these all to work out the right way. Okay, so I want to end. Let's see, I have a few more things to show you. I want to talk about unboundedness for a second. So sometimes your problems are unbounded, and sometimes you want to write down a certificate to show that your problem is actually unbounded. And so we know in the linear and actually quadratic, and recently we know this for the cubic case, could have been later, but Clate has a nice proof for the cubic case, that if your problem is unbounded, you can always write down some ray that's feasible for your polyhedron that the function is unbounded on. Okay? So to describe the ray, you have some feasible point x and some direction d in the recession cone of your polyhedron. And we can say that f of x is unbounded along this ray in these cases. Okay, so I want to show you a distinction here that this is not true in the quartic case. And so it turns out that you can write down a nice little example here in 2 variables where you look at the problem of y2 minus parenthesis y2 minus y1 squared, and you square the whole thing. And you can say, first of all, this is unbounded along the direction y2 equals y1 squared. And you can see that this will zero out the second term, and then you let y2 go to infinity, and it becomes unbounded. On the other hand, what's interesting is that this function is upper bounded along any possible ray. And what you can see is that if you have a linear relationship between y1 and y2, that at some point it will just become unbounded in the negative direction. because of this extra term up here. Okay, so coming back to cubics though, the theorem is that consider an optimization problem with a cubic and linear constraints, that you know it's unbounded, then it's actually NP hard to test whether or not there is a rational feasible array on which the set is unbounded. So this says, there is a nice certificate, or there kind of is for this cubic optimization problem, but it's difficult to test whether I can write it down with rational numbers. Okay, I'll mention there's some history for the quadratic case from the 80s, where, for instance, for the quadratic case, it says that it's NP hard to test whether or not this problem is unbounded. And I think that also follows in some of Avasis's work too. Okay, I'll just end with one example, throw out more examples of things that can go wrong. So we all like SOCPs. They're very nice structured problems that we use in all sorts of convex optimization. And it turns out you can have irrational solutions in these cases that you might want to deal with somehow. And so consider this SOCP, and I want to argue that it has only an irrational solution. And the trick here is, if we use these lower bounds and we square all these lower bounds here, we can actually argue that, you can say that 16 is the sum of all these squares. So 3 squared is 9, 2 squared is 4. And then by these inequalities, you can say, well, this is really less or equal to the sum of the squares. And now if we apply our second order cone constraints, we can upper bound the sum of squares by adding an x0, upper bounding these sum of squares. Now we have these sums of squares. And we can now bound this sum by the square of 4, which is 16. Okay, so we have a nice bound here. And you know that then this sum has to equal 16. Now, if we come back and look at what our lower bounds were, well, this really forces our x0 to take its lowest bound. It forces all these things to take their lowest bound, which means that then x0 takes the value square root of 3, and you have an irrational number. Okay, so that's all I have for today. Hopefully, I've convinced you to be concerned about rationality and polynomial optimization, to think about whether your solutions are actually feasible or if they're just nearly feasible, and think about whether you can write down your solutions in a nice way or not. Our papers are in archive, and I hope we can talk more at the conference about these ideas.